Theoretical foundations. I changed it a little bit from what was on the program. Okay, so to kind of motivate this area, though, of course, Andrea already did a great job of this. So in practice, when we're developing algorithmic solutions to problems in practice, we often have a lot of data about the particular application domain in which we'll be using that algorithm. For example, routing, rideshare, digital advertising, scheduling, et cetera. And the goal in this area is to harness this data to optimize our algorithm's performance on the application domain at hand. So this availability of data has really exposed this new frontier of algorithm design where we can use machine learning to, first of all, improve the performance of existing optimization algorithms, which was really the focus of the previous talk on branch and bound and integer programming. Also, to help practitioners select among different algorithms. So if you have a bunch of different algorithms that you could use for your task, like different SAT solvers or something like that, use machine learning to select among those algorithms. And then we started to see kind of the glimmers of using machine learning to design entirely new algorithms that maybe we haven't even thought of before. So why does machine learning make sense in this context? Just to say a little bit more about this. Well, the routing problems that a shipping company is going to solve are going to change day after day, but not drastically. So demand and traffic will vary, but for example, many aspects of the problems will stay the same. For example, the road network will remain the same. So this means that there's likely some underlying structure which we can uncover with the help of machine learning. And our goal is to use this structure to optimize our algorithm's performance on future problems from the same application domain, but which we haven't already encountered. And by performance, I mean something very general, like runtime or solution quality, memory usage, et cetera. And okay, just in case anyone is, it wasn't in the previous talk, I'll just say my favorite example of this area is also integer programming because of its potential for impact, as Andrea's talk covered. So it's used heavily throughout industry and science. And as Andrea's talk went over, there's tons of different ways that you can incorporate machine learning into solving these problems. And since solving these problems is so difficult, they're NP-hard problems, they can take exponential time to solve, using machine learning in this way can make a huge difference. There's a huge margin for machine learning to help in solving these problems. So this is just one example, like a very nice and concrete example. I took this from Kevin Leighton Brown's tutorial on automated algorithm configuration from ICML 19. So over the years, the US has held these huge radio spectrum reallocation auctions where radio spectrum is bought by legacy holders and resold, hopefully in a more efficient way, to like modern uses of radio spectrum. And these are huge auctions, like moving around billions and billions of dollars. And solving these problems, and by the way, like Paul Milgram and Wilson won the Nobel Prize recently, in part for their work on these spectrum allocation auctions. And actually running these auctions involves solving these huge graph coloring problems. So part of like Kevin Leighton Brown's work in this area was to use machine learning to figure out like what SAT solvers should we use for solving these huge graph coloring problems. So this figure is a little bit hard to see, but along the horizontal axis we have the runtime, and along the vertical axis we have the fraction of these graph coloring instances solved in a given runtime. This red line here is this SAT FC solver, which uses machine learning for algorithm configuration, so configuring these SAT solvers as well as selection, so selecting out SAT solver. The blue line here is the best SAT solver for this problem, and then here is the best MILP solver. SAT is just like kind of, SAT solvers are better suited for this particular problem. But the point is that like using machine learning in this way, they were able to solve way more instances much faster because you can kind of specialize to this particular domain. And their simulations indicated that this use of machine learning for SAT solving saved the government billions because they were able to find much better solutions to these graph coloring problems for these spectrum auctions. Okay, and just going back a little bit, so it's given the potential impact of this area, it has been studied of using machine learning for combinatorial and discrete optimization. It has been studied for a really long time. So this paper, going back to this paper by Rice 76, it doesn't use machine learning, but it kind of started, it was the first to consider the idea of selecting algorithms. So how do I select a good algorithm for my computational problem? Then the earliest paper I know of that uses machine learning for any kind of like discrete optimization task is this old paper from, I think, IJKI 95 by Zhang and Vitercik, who used reinforcement learning for scheduling problems, in particular some scheduling problems that like NASA was facing. Now, around the turn of the century, we started to see some more like data-driven approaches to algorithm selection by people like Carla Gomes and Bart Solomon, as well as related problems like this old paper by Eric Horvitz was looking at runtime prediction of SAT solvers. And then in the kind of early 2000s, there was this boom of research on using machine learning for algorithm selection, like SATzilla, these SAT solver selection, and ML for algorithm configuration for like integer programming and SAT solving. A lot of this coming out of Kevin Leighton Brown's lab. Okay. Now, and then of course Andrea's work talked about a lot of these papers on the previous slide were not using deep learning. It was kind of before the deep learning revolution. And now in the past, say, 10 years or so, there's been a huge amount of interest in using deep learning for discrete optimization. But there are a bunch of key challenges summarized by the fact that machine learning approaches to NP-hard optimization just rarely work out of the box. And they really need to be aligned to the particular algorithmic task at hand. And there are these nice surveys, for example, by Andrea and Yashua Bengio, as well as Kapart et al. On this type of like alignment. So the goal of this talk is to try to isolate and address a few of these key challenges across hopefully 3 different case studies. So let me say what some of these challenges are. So first of all, a major challenge is the decision of which architecture should I use for these discrete optimization tasks. So about 10 years ago, went back in the days of like RNNs and LSTMs, people started thinking about sequence-to-sequence models for things like traveling salesman problem. And then a little while after that, GNNs kind of took over the scene as the main model used for these kind of optimization tasks. But there's a lot of interesting algorithmic reasoning papers starting to come out on using transformers for these types of tasks. And even once you fix the architecture, there's a lot of really interesting questions about like what hyperparameters should I use, things we've seen so far in this workshop of like, oh, should I use sum aggregation, max aggregation of my GNN, which is better suited for my algorithmic task. There's questions of integration. So Andrea's talk covered a lot of this work on like integrating with existing methods like integer programming solvers. But as he also mentioned, you can also think about training your model end to end, and there are like pros and cons of both of these approaches. One of my favorite questions, which we've also kind of heard a little bit about so far in this workshop, is supervision. So how should I supervise on my NP-hard algorithmic tasks when getting a single piece of training data, labeled training data, will require me to potentially solve an NP-hard optimization task? So I think this challenge makes this area one of the most computationally expensive machine learning pipelines out there because, like, yeah, you have to solve an NP-hard problem to get a single piece of training data a lot of the time. Okay, and then robustness. So this is going to be more the focus of this talk is, can we provide any provable guarantees for these methods? And so there have been a few book chapters, for example, by Nina Bolkin, as well as Mitzenmacher and Vasilevitsky on the types of guarantees we can provide. Okay, so my 3 case studies, which I'll hopefully have time to get to all of them, are a couple of ICML papers in the past 2 years. using GNNs for online matching will be the first one. Then I'll look at kind of how kind of uncertainty quantification tools like calibration can be useful in these settings. And then hopefully I'll say a little bit about some neural algorithmic reasoning work, which I know a lot of people here have worked on. So yeah, this first work is joint with Alex Haydari, Amin Saberi, and Anders Wikum, who's here in the audience. Okay, so online matching is a really important problem in many online marketplaces. So for example, in advertising, website visitors need to be matched to ads instantaneously. In crowdsourcing platforms, crowd workers need to be matched to tasks. Rideshare, riders need to be matched to drivers. Medicine, like organ donors to patients, et cetera. And the primary challenge here in online matching is that you need to make these irrevocable decisions online without precise knowledge of how demand is going to evolve. So in this paper, just to give you a kind of overview of what I got to talk about in this section, we train a graph neural network for a particular matching model, online Bayesian bipartite matching. There are many different models of online matching, but I'm going to tell you more about this OBBM model. Well, so the challenge with OBBM is that the optimal online policy, it takes exponential time to compute. But we are going to supervise with this exponential time policy. But we'll leverage the size generalization properties of graph neural networks to train on tiny graphs and then test on large graphs. And we'll see that this GNN outperforms various baselines on various graph data sets. And then my favorite part of this paper is the theoretical contributions, where we tried to justify why do GNNs make sense for this OBBM problem. GNNs are inherently like a polynomial time function or algorithm, whereas OBBM, as I said, the optimal online policy takes exponential time to compute, but we'll try to theoretically justify why this still makes sense. And the key challenge, like I've been alluding to, is just the sheer complexity of the optimal online policy. So it's known that it's NP hard to provide a constant factor approximation for some constant to this optimal online policy. Okay, so let me tell you about this particular matching model. So there's going to be a bipartite graph with offline nodes and online nodes, L and R. So for example, the nodes might represent crowd workers and tasks. Now these offline nodes, we're going to assume in this model that they're there at the beginning of time. So the crowd workers are all there at the beginning of the day, but the tasks are arriving online. And the edge weights represent the payoff for a given worker to complete a given task. So each online node is going to arrive with some probability. So at time 1, this, say, sweeping node 1 will arrive with some probability p1, or it just simply won't arrive with some probability 1 minus p1. This next, like, computer-related task will arrive with probability p2 at time step 2, or just won't arrive with probability 1 minus p2, et cetera. Okay, and so if this node t arrives at time step t, which happens with probability pt, we need to irrevocably decide, should I match this node with some available offline neighbor, someone who hasn't been matched yet, or skip it and just not match it to any node? And the ultimate goal is to compute a high-weight matching. Okay, so I'll tell you a little bit about the optimal online algorithm for this problem. So let's say we're at time step 2 now in this picture. We've matched this sweeping task to this guy. So that's the blue line here. And I'm going to say S is a set of offline nodes that are still available at this round. So it would be this lady and this guy here. So this optimal online policy computes, it's like a huge MDP, essentially, a very expensive MDP. So it computes the Bellman, or value to go, function, which I'm going to denote as VG, G is the graph, S, T, S is a set of offline nodes available, and T is the time step. And so this value to go is the expected value of the max weight matching achievable on this graph. And the expectation is over the future arrivals, so time step t up to time step however many online nodes there are. And the matchings are just restricted to those available offline nodes, S. And the optimal online, it's just a MDP, so it selects the action that maximizes the value to go. So just to say a little bit more about this, you could say the value of matching to node U, offline node U, available offline node U, is like the edge weight between the node T and node U, plus the value to go of, okay, so now U has been matched, they're no longer available, we remove them from the set S, and we increment the time step T to T plus 1. Or we just skip it, we leave that crowd worker to a future task, and the value of skipping, well, the set of offline nodes will remain the same, and we'll just increment our counter. Cool. So let me tell you about our GNN setup. We call this Magnolia, matching algorithms via GNNs for online value to go approximation. So we start off with our matching state. So we're at some time step. Some nodes have already been matched, like here. So some node has just arrived, and there's some nodes that haven't yet arrived, together with a skip node. If you match to the skip node, you're just skipping you. We add node features, things like, has this node arrived? Is it online or offline? Probability, these PTs, et cetera. And I'll mention this at the end of the talk, but I think it would be really cool to extend this pipeline to need fewer of these features, or even less knowledge of the graph. That would probably require a very rich graph data set. I think that would be really cool if you could just learn these things. We do show that our pipeline is robust to noise in these parameters, but so then we run this attributed graph through a GNN. We use the GenConv architecture. It seemed to work well according to ablations. And then we predict what I'll call the marginal value to go. So we supervise with this marginal value to go, which is just the value to go of matching with a given node, U. So for each node, we're predicting this value, minus the value of skipping, just skipping and not matching this online node to anybody. And so yeah, for every offline node, together with a skip node, we predict this marginal value to go, and we simply match to the node with the highest, the available node with the highest predicted value to go, which in this case, I guess, would be this yellow node, highest marginal value to go. This guy has already been matched, the first node. Okay, so I'll tell you a bit about our data sets now. So we look at various random graph families like Erdős-Srény, Barabási-Albert, some random geometric graphs, as well as some semi-synthetic graphs based on GMission, which is based on some crowdsourcing data, together with a semi-synthetic rideshare setup using this really nice OSMNX library, where we kind of sample riders and drivers from street maps. Okay, so these are, I'll walk through these graphs slowly. This is just kind of a highlight of our experiments. We have more in the paper, but I'll just highlight some. So we have Erdős-Srény, random geometric, rideshare, and our crowdsourcing one. Okay, and so along the vertical axis here, we have the competitive ratio averaged over our test set. So competitive ratio is the weight of the matching that the algorithm returned divided by the weight of the offline optimal matching. So we train on really small graphs because, again, we're supervising with marginal value to go, which takes exponential time to compute. But we train on these graphs of size 16. And here along the horizontal axis, you can see the size of the graphs we're testing on. So it's still fairly small graphs. We were kind of limited just by the memory constraints of the GPUs we were working with. We have higher memory GPU access now, so we're going to scale these up for the journal version. But in any case, we're testing on graphs with a 2-to-1 ratio of online to offline nodes, which is kind of like a more interesting regime for learning, because you have to be really careful of whether you're skipping or matching.
So 2-to-1 means
the
people are half of the task.
Or the task, you have double as many tasks as people. Yeah. Okay, and now what are these colored lines? So greedy, the blue line, selects the highest weight available edge at every time step. Greedy T is a little smarter. It selects a greedy edge if the weight exceeds some threshold chosen via holdout set or validation set. And then LP rounding is this Braverman et al. 0.63 approximation algorithm based on LP rounding. So that's the green line. And I guess the takeaway is that in general, Magnolia, Magnolia we don't retrain for each of these. We just have a single Magnolia GNN, and it works well. And it works well when in regimes where other of these methods struggle. So yeah, this is just like a highlight of the results, but I want to move on to the theory guarantees as well, where we're trying to answer the question of why are GNNs well suited for this matching problem. And the intuition is that most practical instances are well structured. And we show this rigorously for this class of random geometric graphs. In particular, we prove that under these families, this value to go function is nearly local. And these random geometric graph families have been used in a lot of different applications, a very common graph model for like spatial matching problems, opinion dynamics in graphs, contagion and wireless networks, et cetera. So we show that VTG is nearly local, and then it's already known, it's just by definition, that graph neural networks compute local functions. So there's this nice kind of structural relationship between the types of functions that approximate value to go, local functions included, as well as the type of functions that GNNs are actually able to compute. So now I'll say a little bit more about this. So first, random geometric graphs. So random geometric graphs are defined, we're looking at bipartite graphs, so we still have the left hand and the right side hand of the graph. D is a distribution over a metric space, as I'll say in a minute, and delta is a scalar. So the first thing that we do is draw feature representations for each node in the graph, the left hand and the right hand side. In this talk, just for notational simplicity, D is going to be the uniform distribution over the unit hypercube in D dimensions. But we generalize this in the paper to any distribution over this hypercube that's like not too, that's kind of smooth. So, and we connect two nodes, offline and an online node, if the difference in their feature representation is small. In particular, we look at the L infinity norm and say it needs to be smaller than some capital delta, which is a parameter of this distribution. Okay, so as I said, GNNs learn local graph functions. This is just kind of by definition. So this is just to be clear what I mean by a local function. So a function f over graphs is R local if this function only relies on info from, this is just in words, first I'll say in math in a second, but if this function only relies on information in the R-hop neighborhood, which I'll denote as NR of V for each node V. And just a bit more formally, what I mean by that is that there are these functions, phi and psi, such that this function f applied to G is basically like you apply the function phi to these functions, these values which are like psi applied to the neighborhoods, like each of the R-hop neighborhoods in the graph. And it's just an observation, it's known GNNs with L layers compute L local functions because they're just doing message passing on their L-hop neighborhood. Okay, so now value to go, I claim, is locally approximable. So what do I mean by that? So we'll say that a function f is R epsilon delta locally approximable, or LA for short, over a graph distribution G if there exists a R local function, H, such that f of G and H of G are just like close up to some multiplicative epsilon. And this needs to hold with probability 1 minus delta over the draw of a graph from this distribution. And And just an informal version of our main theorem of this paper, we show that for any epsilon delta between 0 and 1, and capital delta, which was this kind of threshold defining the random graph model, so long as this delta is sufficiently small, this value to go function is log size of the graph epsilon delta locally approximable over this random geometric graph distribution. And I guess one thing that's nice, of course, like with GNNs, we often train GNNs with only a constant number of layers. We were at least happy to get just like a logarithmic number of layers in this bound. But I think it would be really cool if you could show like, oh, for a GNN, like a local function with a constant number of constant size neighborhood radius, maybe you could show like some approximation guarantee or something like that. Uh-huh.
Let me start again.
Sure.
You do not know if a GNN can approximate every R local function, right?
Yeah, I think that something that we want to do seems possibly within reach. We just have to kind of like maybe sit down and do it, is show that like in particular the R local function that approximates value to go can be expressed by like a GNN with these hyperparameters and things like that. Yeah, we think maybe it's within reach, but we'd be really, it would be nice to show that. Uh-huh.
So this is very nice. Do you know that whether you can relax this random graph, this random geometric graph a little bit? Because this is only one dimension. Can you add a few long-range edges by adding a small Erdős running overlaid on top of that, still get this result?
Yeah, probably first.
Even more practical.
Yeah, I think first you'd have to like I guess think carefully about like what the P is of the Erdős. But yeah, there should be some relaxations. Yeah. And just a little bit on the proof intuition, we show that for these random geometric graphs, they can be split into clusters with few intercluster edges. So just like intuitively, if we're here in Berkeley trying to get a Uber, we certainly hope that our Uber is coming from Berkeley and not coming from San Francisco. So like it's like you can split, it makes intuitive sense that your rideshare instances can be like split into these local neighborhoods with few edges crossing between neighborhoods. And then we show that like if you just focus on matching or like within the clusters, this is like nearly optimal. And so you can compute this online optimal matching with using a local function, or at least approximately. Okay, so yeah, just to summarize, we get this nice kind of structural correspondence between the types of functions GNNs compute, which are these local functions, and the types of functions that can approximate value to go, which include these local functions on random geometric graphs. So just a takeaway from this section, we looked at graph neural networks for online matching, NP hard, but lots of applications in many different market design settings. We were able to supervise using this exponential time online optimal policy by training on small graphs and testing on large graphs using size generalization properties of graph neural networks. And we developed some theory to try to understand why are GNNs well suited for this online matching task. Mm-hmm.
So is it still NP hard on your graph class?
Yeah, I don't know actually. Yeah, interesting question. Yeah, I would say that our result is very like kind of existential. Like we show there exists this cluster, this kind of partition of the graph into these clusters. So yeah, you'd have to think about like, yeah, can you actually recover? Is it also computationally efficient to find that clustering? Yeah, which maybe it is. But the nice thing, I guess, is that the GNN seems to kind of just do that for us. So yeah, overall, going back to these major challenges, it's at least starting to answer some of these questions of like architecture. Can I understand what architectures are good for these combinatorial tasks? Integration. Here we kind of like integrated with this MDP. So kind of replacing this computationally expensive Bellman equation computation with a GNN. It's kind of similar to replacing like strong branching in integer programming with a GNN. Supervision, we use the size generalization property to supervise on this MPR task, and then we tried to provide some kind of theoretical guarantees. So now I'm going to move on to the next part of the talk, which is algorithms with calibrated predictions, also with Anders and also with a student, Judy Shen. And here I'm going to focus a little less on architecture and supervision, but it will be much more kind of in depth, I guess, about the theoretical guarantees. Okay, so this area of algorithms with predictions has come out of the observation that in practice, many aspects of our input are unknown a priori. And like as we just saw in the first half of the talk, future traffic or demand and rideshare. And however, these things like demand are often predictable in some sense. So we often could have some predictions about our problem. So for example, this value to go of matching a rider and a driver we showed seems to be kind of predictable. Another nice example would be in caching. Maybe you have some prediction of the next time you're going to see some element in your memory. And the main goal in this area is to use these predictions to improve algorithms' performance. And this has led to this research area called algorithms with predictions, which has been summarized, for example, by this book chapter by Mittenmacher and Vitercik. Oops. Okay. Okay, so I just moved this to the top. So the theoretical goal in this area is that we want algorithms which have performance that should, first of all, improve with our predictions quality. So if we have really good predictions, hopefully our algorithm performance is going to be really good. But the most important thing is this robustness guarantee. Our algorithm's performance should ideally never be worse or much worse than the best known worst case algorithm. So even if the predictions are terrible. And this kind of framework was suggested in this paper by Licouris and Vitercik a few years ago. And I think this robustness guarantee, although this algorithms with predictions area has been really extensively studied more from a theoretical perspective, I do think this robustness guarantee actually is quite important in a lot of kind of high stakes applications. For example, with my student Mika, we've been thinking about these problems in the context of organ allocation systems, where in like medical domains, you certainly want to be robust against terrible predictions because it's such a high stakes setting. Another example where this framework has been used in practice is like in energy systems, where a lot of energy systems is algorithms are built on forecasts of demand, but you really want to be robust against bad predictions because it could lead to like power outages and things like that. And so this algorithms with predictions area has been studied for many different problems, many on graphs, like routing, flows, matching, et cetera. I'm not going to talk about graphs in this part of the talk, but I think some of the ideas could generalize to graph problems. And so the main challenge, I guess, that this area tries to deal with is that your prediction errors can really amplify when they're used in downstream decision making. So you should not just blindly trust the predictions. Clearly, this would be kind of catastrophic, for example, in like an energy systems application. So our insight in this paper is that machine learning models can estimate, modern models can estimate uncertainty automatically through tools like calibration and confirmable prediction. These give very well-defined statistical notions of whether a prediction can actually be trusted. And so our goal is to like leverage this uncertainty quantification area to tell us how much can we actually trust our predictions or not in the downstream decision-making task. So just a summary of what I'll talk about in this part of the talk. We demonstrate calibration's utility through 2 case studies. First is this classic online rent or buy problems, where you're trying to like decide, should I rent some resource like a cloud computing resource over time, or should I just go ahead and make a big upfront purchase of some GPUs or something like that? And we give an algorithm with guarantees that improve based on the accuracy of our predictor together with a calibration error. We also look at online job scheduling, motivated by problems in like radiology and diagnostic imaging. And we show that using calibrated predictions yield better schedules than prior work, which didn't kind of look at this calibration issue as carefully. And we validate our methods on real-world data sets. So just a tiny bit about some additional related work. There have been a growing number of papers recently that look at probabilistic or distributional predictions, but not looking at this issue of uncertainty quantification or calibration too much. There have been one paper that looks at, can we learn the prediction's reliability online? So we're looking at an offline problem, but related. And the most related to ours is this paper that looked at algorithms with conformal ML predictions, another uncertainty quantification tool. But we show in the paper, I'm not really going to get into this here, that calibration has key advantages over conformal methods, especially when our predictions have high variance. Yeah, it's basically when I give you a prediction together with a confidence interval, saying with 99% chance the true value is in this confidence interval. But if your predictions are high variance, or if the quantity you're trying to predict is high variance, these conformal intervals will be huge, maybe not too meaningful. Okay, so now just a little primer on calibration. I'm just going to talk about this for a binary prediction target. So in calibration, let's say we have some random variables, x and y. So with some port x is like our features and y is our target, 0, 1 binary target. We say that our predictor f is calibrated if the probability that our true label y is 1, conditioned on the event that our prediction f of x is equal to p is equal to p. So let me give you an example, like rain. Let's think about rain prediction. So a calibrated predictor will tell us that the weather will be rainy on 50% of the days where our predictor predicted 1/2. The weather will be rainy on 100% of the days where our predictor told us 1. And it will be rainy on 0% of the days where our predictor predicted 0. So if we get a prediction of 0 and 1, we're like, okay, I have high confidence that it's going to be rainy or not. If we get a prediction of 1/2, then it's just kind of like a coin flip. So a calibrated prediction tells us how much we can trust the prediction in some sense. And calibrating an ML model can be easily accomplished, sometimes just by defining the right loss function or doing some like post-processing steps. Okay, so I want to say a little bit more about calibration, which will be useful later in this talk. So let's say that t of x is the probability y is equal to 1 conditioned on our prediction. And just as a sanity check, this will equal f of x if our prediction is perfectly calibrated. So there's this nice decomposition of our predictor's L2 error, which I have here. We can decompose this L2 error into, first of all, the inherent uncertainty of the thing that we are trying to predict, the variance of y, minus what I'll call the sharpness, which is the variance of this conditional probability, and then plus the calibration error. I said if our predictor is perfectly calibrated, t of x will equal f of x, and this calibration error just in this case is just telling us like what's the L2 difference between these things. And so there's this kind of range of calibrated predictors. You can have a perfectly calibrated, but totally, not very informative prediction, very unsharp prediction of simply the probability that your target y is equal to 1 for all possible x. So not taking into the account the input features at all, just predicting the mean. You can also have a calibrated, very sharp predictor, which is just the Bayes optimal predictor. And this is very informative, but likely just very hard to learn most of the time. Okay, so this sharpness will be important later in the talk. But let me start with our case study, online rent or buy. So these online rent or buy problems model this rent or buy problem under an unknown horizon. So we're trying to balance this upfront cost of say buying a bunch of GPUs versus incurring some ongoing like rental expense of like cloud compute credits. So yeah, these types of problems are ubiquitous in practice, like in cloud computing, equipment renting, mobility, like bike share, buying a transit pass, facilities, and software, like should I get a monthly subscription or some annual license or things like that. And I'm going to talk about this problem in this canonical language of the ski rental problem, which is like this, just a language for this prototypical online rented by decision-making problem. So in this problem, a skier is going to ski for some unknown number of days. Maybe they don't know how much they're going to like skiing or how long the ski season is going to last. Z is the unknown number of days. And each day they need to decide, am I going to rent the skis for one more day, or am I just going to buy them today for $B and never rent again? And the goal is to minimize the total cost. So this famous paper by Anna Carlin et al. Gave this worst case break-even strategy, which says rent for B days, and if you still want to keep skiing, buy on that Bth day. And you can show that, easily show that the competitive ratio of this policy, and again, competitive ratio is how much did the algorithm pay versus how much did the clairvoyant strategy, which knows Z in advance, how much would it have paid? So yeah, amount algorithm pays, and down in the bottom here, you can see, well, if you know that you're gonna wanna ski for fewer than B days, you should just rent every day. If you know you're going to want to ski more than B days, you should just buy the skis at the beginning of the season. So we have min Z B, and if you do that algebra, you get that this is less than or equal to 2, and also no deterministic strategy has a better competitive ratio. Okay. So a little bit of prior work on this problem. So like Ravi Kumar et al. Looked at this problem where you get a prediction of the number of skiing days Z. And this algorithm is based on this trust parameter lambda. And so this needs to be set by the user, but it's basically saying, okay, if you fully trust the prediction, if you think it's perfect, set lambda to be equal to 0. And if you don't trust the prediction at all, set lambda to equal to 1. And if you kind of trust the prediction, maybe find some intermediate value of lambda. And the algorithm or policy is really simple. It says if my prediction, if my prediction of how many days I'm going to want to ski for is greater than B, then buy on day lambda B. So if I think I'm going to want to like skiing, I won't buy on the very beginning, but I'll buy kind of sooner than the break-even strategy. If I don't think I'm going to like skiing, then I'll wait longer to day B over lambda. So it's a very intuitive policy. And what they prove is this consistency guarantee, which says if your prediction was perfect, so if you exactly knew how many days you were going to want to ski for, then you get a competitive ratio for using this policy of at most 1 plus lambda. So if you knew a priori that you should have trusted your prediction, you can set lambda to be equal to 0, and you get a perfect competitive ratio of 1. We also get a robustness guarantee, which says that any prediction, no matter what, will yield a competitive ratio bounded by 1 plus 1 over lambda. So again, if you knew you couldn't trust your prediction at all, you could have set lambda to be equal to 1, and you would have just recovered the break-even strategy with a competitive ratio of 2. And this kind of trade-off between consistency and robustness using this lambda parameter is tight. But maybe we don't know in advance necessarily without uncertainty quantification tools, like how much can we trust our prediction. And so our goal is to leverage these uncertainty quantification tools to automatically encode how much we can trust the predictions. So a little bit more technical detail. So X is going to be our skier's features like age, gender, things like that. And we're going to have a predictor f of x of our target y, which is this person going to want to ski for more than B days, with a max calibration error of alpha. So max over all possible v in the range of our prediction, predictor f of v minus this conditional probability.
So you want to binary prediction to be Z bigger than B, or you want to predict the number of days?
We're going to do binary here. Yeah.
So you want to do a classification to say bigger than Z than B or less?
Yeah, and calibrated being the important thing.
Okay.
Yeah. And so our policy is simple to state right now. So given a prediction f of x equals to v, you're going to want to rent for some function k of v days. Now, the actual function k of v is a little gnarly, but it's maybe simpler to look at this plot. So here I have v along the horizontal axis, and along the vertical axis I have the number of days rented, this k of v, when b is equal to 5. So we just chose a particular value of b to plot this. And so what you can see is that, so if our prediction is 0, it's saying, okay, almost with certainty, you are not going to almost with certainty, let's say with alpha is equal to 0, so no calibration error, you are not going to like skiing. So you should just rent however many days you end up skiing. Now, on the flip side, if v is equal to 1, we're saying with certainty and alpha is equal to 0, you're going to love skiing. And so you should just buy at the very beginning. And for intermediate values of v, we interpolate between these two extremes. And you can see as the calibration error increases, we kind of hedge against this decision of buying right at the beginning. And so these are the bounds that we get. So first, a prediction-wise bound. So here's our competitive ratio conditioned on a prediction of v. So this is a formula, but again, probably easier to look at the plot. So here we have v along the horizontal axis and the competitive ratio along the vertical axis. And you can see, let's look at alpha is equal to 0. So again, this means no calibration error. When we know we're going to love skiing or hate skiing, 0 or 1, we can get this perfect competitive ratio of 1. As we increase the uncertainty in this intermediate range, we interpolate between this perfect competitive ratio of 1 on either end. But the kind of nice thing is that the max of this function is something like 1.8. So with this additional bit of information about the underlying distribution of the ski rental problem, we're able to beat that kind of 2 competitive ratio lower bound. But as the calibration error increases, this function just kind of like moves upwards. The competitive ratio gets worse. Okay. We can also show that this is essentially optimal with a nearly matching lower bound. And we also get a global bound where we just like integrate over what we're conditioning on. And I guess the takeaway of this global bound is that lower mean squared error and better calibration error will lead to, like if alpha is equal to 0 and you have 0 mean squared error, then you get a optimal competitive ratio of 1. And our bound increases with mean squared error and calibration error. Okay. So one last case study, which I'll go into in a little higher detail. So this case study was motivated by a radiologist scheduling problem, where we have one radiologist and they have some backlog of imaging cases. Each case has some true urgency, which is initially unknown. But as the radiologist kind of starts to review the case, the urgency of the case is revealed to them partially through the review. I'll explain this in more details on the next slide, but just a high level. Our machine learning model gives noisy urgency probabilities, but these predictions can be wrong. And so we need to choose the order in which we're going to process this backlog of imaging cases. And we want to develop some simple but robust scheduling policy that is robust against these bad predictions. So in a little more detail, I'll just kind of zone out to online job scheduling now with that motivation. We have one machine that needs to process n unit length jobs. And each job I has some unknown priority, 0 or 1. And if we process either unit length jobs, but if we process a theta fraction of the job, it will reveal its priority. And our jobs can be stored after partial processing. So we can partially process the job, discover its low priority, then put it to the back of our list and process it later, finish processing it later. And our goal is to minimize the weighted sum of our completion times which is basically the sum over all of our jobs of the completion time of that job starting at time 0. And then here we have a weight, a cost per unit delay. Yi is the priority of the job, and delaying a high priority job is more costly than delaying a low priority job. So setting this up with predictions, X is going to be some features of the job, and we're just going to have this binary predictor of is this job high or low priority. Just a little bit about the scheduling strategies. We can either do preemptive scheduling, as I mentioned, where we can start a new job if we discover that their current job is low priority, or non-preemptive, which means that we always process our open jobs to completion before moving on to the next. So our strategy will kind of interpolate between these two. So I'll tell you about the kind of baseline policy that we're going to build on, which is from this paper by Cho, Schmois, and Henderson. So the input to this policy are probabilities pi that a job I is high priority. So beta, and we're going to define some threshold beta based on, again, like this partial processing theta and the weights per delay of these jobs. But just some thresholds. Now we're going to order our jobs by the priority that by the probability that they're high priority. So I1 is the job with the highest predicted priority. And M is going to be the number of jobs whose predicted priority is greater than this threshold. So it's basically just like a thresholding rule. We're going to now run the first M job. So basically the jobs that we have a predicted priority greater than beta, and we're going to run them in order of the order we defined in step 2, preemptively. So if we discover a job is low priority, we're just going to move it to the back. Then, okay, we've done that for the first M jobs. Then we're just going to complete the remaining jobs non-preemptively in order. And we're going to ask the question, what if the predictions are calibrated? So Cho et al. Didn't talk about calibration, but if you look at what they're doing, they actually are looking at a specific calibrated but very unsharp predictor. Whereas what we're going to ask is, okay, what if we have an arbitrarily calibrated but sharp predictor? Kind of what is the value of sharpness for this scheduling problem? And the key insight is that interchanges are the primary source of regret, where regret is the weighted sum of the completion time of our algorithm versus the optimal ordering in hindsight. And what do I mean by interchange? I mean processing a low priority job, maybe even just partially before the high priority jobs. So this is very intuitive, that interchanges are the source of regret. But what we show is that sharp predictors lead to fewer interchanges. And so we can actually quantify the value of having sharpness in the downstream combinatorial objective that we're trying to optimize. So just a figure to illustrate this. Let's imagine these are our predictions, P1, P2, P3, of a sharp predictor, f of x. Whereas these are the predictions of some unsharp predictor, f prime of x. So they are calibrated there, but they're kind of maybe predicting some conditional mean, not extremely informative, where these sharp calibrated predictors are telling us something far more granular about our job's priorities. Now imagine here's 1, here's 0, and here's our threshold beta, which defines how we process the jobs preemptively or non-preemptively. Intuitively, with this, or not even intuitively, with this unsharp predictor, these jobs, which are all predicted at the same value, are just going to be processed in some random order. And these other jobs are just going to be processed in some random order. Whereas with our sharp predictor, we'll process jobs in a much more less random way, a much more informed way, using the granularity of this sharp predictor. So I think I'll skip ahead a little bit in the interest of time, but our main result is that we kind of specifically quantify what is how sharp a predictor is by looking at the variance of the predictor. And we show that we can bound the number of interchanges of our policy by some values that depend on the irreducible uncertainty of the thing we're trying to predict, the false negative and the false positive rates, and then subtracting out the sharpness of the predictor. So as the predictor gets more sharp, the number of interchanges improves, so we can actually like quantify how much sharpness is improving the outcome of this scheduling. Okay, and yeah, we eventually get a bound on the algorithms workout, but I'll leave that to the paper. And finally, we have some experiments on predicting sepsis onset to improve early detection. And so we quantify, indeed, the how much better is like our scheduling regret using an unsharp predictor together with a sharp versus a sharp predictor. And the sharp predictor leads to better regret. Okay, so yeah, the takeaways are that calibration is a really valuable tool for algorithms with predictions. We saw this through a few case studies. And we give performance guarantees that improve with the calibration error and validated our methods on real-world data sets. So in the interest of time, I'm unfortunately going to skip over this final section, but we have this nice paper with Hayu, who's in the audience, on some neural algorithmic reasoning in the NP-hard domain. And I'll just skip ahead to the future work. Okay. So I wanted to kind of compare and contrast, first of all, neural algorithmic reasoning, because so many people in the audience here have worked on neural algorithmic reasoning, versus its algorithms with predictions. Like, are there any connections? What are the differences? So in neural algorithmic reasoning, as we saw maybe yesterday in some of the talks, so we see neural algorithmic reasoning, the goal is really to learn algorithmic behavior from data, from traces of algorithm. And it's nice because you can incorporate this kind of encode, processor, decode architecture to incorporate real-world features directly into this end-to-end differentiable pipeline. And we've seen it often scales to real-world graphs, and there's some new theoretical results trying to understand how and why. However, in general, the neural algorithmic reasoning community has kind of not focused more on formal guarantees. Of course, there have been some papers, but it's mostly been about like training this end-to-end differentiable pipeline. Meanwhile, the algorithms with predictions literature that I just surveyed a work in, some positives of it is that it retains the formal worst-case guarantees of worst-case analysis, which gives this robustness against bad predictions. However, I think a con of often in this area is that the predictions themselves can often be very hard to learn, maybe not even learnable by any ML model. And there's way less research into leveraging real-world machine learning, like real-world rich features. And so I think a really nice future direction that people in this audience might be interested in is connecting these two regimes to really leverage the end-to-end differentiable pipeline of neural algorithmic reasoning papers, while perhaps providing these theoretical guarantees for the learned algorithm. I think there could be a lot of like really nice synergy between these communities, but they've been almost entirely distinct up until now. So now a little bit more, just a few more future directions. So in online matching, as I mentioned, I think a good future direction is just like more unknowns. The graph structure, arrival probabilities, edge weights. But I think this will require really rich data sets where these can be learned from features, which I think is a bottleneck at the moment. Moreover, I think our locality analysis from that paper, honestly, is not too specific to online matching. I think it could apply to other combinatorial problems that exhibit some kind of like intuitive locality structure, like max cut, where intuitively, like you can probably piece together local solutions to max cut to get an approximately globally optimal solution. Another direction related to the second half of the talk, this algorithms with predictions, kind of related to this neural algorithmic reasoning direction I mentioned, is to further open the ML black box of algorithms with predictions and analyze how predictor properties impact the downstream algorithmic decisions. So in this talk, we saw like mean squared error, calibration, sharpness, and like inherent uncertainty, and how they impact the quality of the downstream combinatorial decisions. You could also think of other properties like false positive versus false negative rates. And here I think the ultimate goal would really be to guide both the model choice as well as how do we actually train these ML predictors for these downstream combinatorial tasks. So with that, I'll wrap up. Thank you for your attention and questions.
Questions? More questions for Ellen?
Out of curiosity, for the first application, did you try reinforcement learning algorithm instead of supervised learning? And is there any chance that the kind of guarantee you have on the fact that you can approximate the reinforcement learning setting where you are not supervising, you could approximate it too?
Yeah. And we didn't explore reinforcement learning, but yeah, I guess one nice aspect of using the supervised framework is that likely training is converging much faster. Despite that we have to get these exponential time labels, I do believe the overall training pipeline is faster than an RL pipeline. So that's one benefit. But I think yeah, there's certainly many other strategies that one could try to train this thing.
Other questions? If not, thank you again.
Thank you.
We resume at 1:30. 1:30. A good lunch.